Okay. We're getting down to it. The final exam is coming up 2 Saturdays from now. Everyone in here is obligated, right now, everybody's obligated, including special study group leaders. If you're a special study group leader, you still have one more session to do, and then you'll be excused from the final. Otherwise, the rest of you, if it's supposed, Saturday afternoon is supposed to be the free period of exam week. So, in which we're supposed to be allowed to have multiple section final exams. But double check your schedule for conflicts. Now, by this, I don't mean tailgating party out at the stadium. That's not a conflict. Okay, but if another professor is giving you a final exam at 1 o'clock on Saturday afternoon, that would be a conflict. And let's tell your instructor, if that is you, to contact me. We'll work out some kind of a deal. That's normally how we do it. Okay, so that's 2 Saturdays from now. And it's clicking right along. Here's our outline for the day. Our last Will Rogers quote of the semester. If I studied all my life, I couldn't think up half the number of funny things passed in one session of Congress. Very nice. Now, a couple things I want to go over with you, and that is, first of all, best 2 out of 3 midterms is up, and that is about all that is up. I've had an extremely Thanksgiving vacation, right? Didn't end up being much of a vacation, and it carried over until, about 10 o'clock this morning, so a lot of stress for me. But anyways, I did get this up, and let's take a close-up look at it. So basically, you now have all your exam data. So for instance, here's exam 1, and then that's a 45. You might want to jot this down as an example. And then here's exam 2, and that's 41 for this student, this imaginary student. And then zip down here, here's the last one, exam 3, and this student got a 42 out of 50. So there's my 3 exam scores. Now one of them we're going to chop, that's the 41. So jot that down and then put an X through the 41. That's the dropped exam score. Now, if you keep all 3 of those, it's an average of 85.3. But that's not what we do. We drop the lowest and keep the best 2. So instead of 85.3, what you get is down here at the very bottom. Best 2 out of 3. And for this student, in this example, it works out to 87. And that is nice. All right? If you have 3 different scores, then your average will go up as soon as we drop your lowest score. Now, if you have 42, 42, and 42, all the same, then dropping one of those is going to keep you at 84%, 42 out of 50. So, but if you have any difference in your scores, then it's going to improve your average. Also, if you have missed one exam, and that counts a few of you, then that missed exam is the one that gets dropped. So we'll keep the 2 that you do have. Now that's not very many of you. Almost everybody is in this situation. All right, 80-something%. So it's looking pretty good. So as I always say, that this is a very nice benefit. And the problem is you don't see how nice of a benefit it is until the end of the semester. Okay? Now, questions about this? I'm not sure about you guys, but I'm ready for Christmas vacation already. We just had Thanksgiving vacation, and I'm already ready for another one. It's my first day. That's bad. My first day back. I'm already ready for another vacation. All right, SSG leaders, get your date and time info date, time, and location info to me ASAP. And just to reinforce you SSG leaders, it can be a completely different location, different time, and it will be a different day. So that's all up to you. The rest of you guys, we are going to do sign-ups Thursday night. All right? And I'll try to get the schedule sheet going today and tomorrow. And then Thursday, we'll talk about it. Hopefully, I have all the SSG leader info in there. Thursday for class, we'll talk about it for a few minutes. And then Thursday night at 7 p.m., you'll do your sign-up. So that's the Raging Buffalo Stampede on Thursday night at 7 p.m. Okay, questions about that? Yes. Messaging inside SSG leaders, you can message me. You don't need to print out another thing. Just message me day, time, location, and distinguishing, same info as before. And it can all be different if you want. Another question. Okay, let's keep going. This is a scary picture from The Lord of the Rings. Do you remember? Did you see that? Remember seeing that? Grand. Big. In Latin, that's called oppugnat molibus urbum. And Brandon? It's Latin. In quotation, the phrase there is Latin. And it's actually related to something that we're going to study today, molecules. Okay? Molecules, moles, cules, etc. Now, oppugnat molibus urbem. Molibus, the middle word there in Latin, comes from the Latin root word moles, meaning shapeless mass, huge bulk. Okay? And that phrase literally means attacks huge bulk on city, urbum. All right, so this is a cool picture. So in other words, a big battering ram punching your fist into the city gates or what have you to get your way in, a siege tool. All right, so that's a Latin phrase that uses the M-O-L-E root word that we find in molecule. Now, the suffix cule is, you can look it up at dictionary.com. And by the way, I have a bunch of links to these various terms in additional readings, in case you haven't noticed. That means smallness, cule. So something cule. It means a small something. So a molecule means a small part of a shapeless bulk. Okay? And it's basically a word that we have developed based on the conviction that this huge bulk of atmosphere that we're sitting in is composed of little unseen cules, molecules of oxygen, nitrogen, CO2, a little bit of argon, a little bit of, a bunch of other different gases and stuff, mostly oxygen and nitrogen. And that's shapeless. The atmosphere is, actually, I should say the atmosphere is shapeless. It doesn't have a covering. It doesn't have a box. It doesn't have a container. It's roughly spherical in shape, like a spherical shell surrounding the Earth, but the Earth is not a perfect sphere. Anyways, we could call it a shapeless bulk. A molecule is a small part of that. For instance, good old NH3, ammonia. Go ahead and make a sketch of that. The blue sphere there is to represent nitrogen. The three white spheres are to represent hydrogen atoms. They're bonded together. And those two little dots up there, those represent electrons that are repelled to the upper part of the nitrogen atom, making ammonia kind of a polar molecule. Kind of like water. Water is a polar molecule too. So that's what those two little dots means. All right, so molecule, moles, cule, all that stuff. Atomic mass unit, page 230. Let's talk about that. The atomic mass unit is also related to moles, molecules. And the formal definition on which the atomic mass system is built, you know, they originally thought, well, let's use hydrogen and call hydrogen equal to 1. And then some people said, well, there's not much hydrogen. You know, let's use oxygen. It's a little bit easier. So make oxygen 16, and then everything else is, you know, lower than 16 or greater than 16 based on that. But now what we do is we use the carbon-12 mass, and 1/12 of that is exactly one atomic mass unit, the AMU. Now, if you go and look at the periodic table, there's something, you know, the top is the word carbon. That's the name of the element. 6 is the number of protons in the nucleus. Capital C, that's the symbol, the chemical symbol. It's one of the easy ones. And the atomic mass, 12.011. Now let me ask you, is there anything about that that seems a little unusual to you? Look at that. Look at the information in that small rectangle of the periodic table. Does anything catch your eye as being, what? Look, I don't see everybody looking. I see people gabbing over there. Look at that. Yeah, look at this screen. Come on, think. Use your eyes and think. What do you see?
The atomic mass has a 0.011.
Yeah, what is this? What's up with this? Why isn't that exactly 12? Atomic mass unit, carbon 12. All right, so go ahead and write down this question. Why is the atomic mass for carbon not exactly 12? And if you look at a periodic table, that's the number you're going to get. And if the atomic mass system is based on carbon being equal to 12, then how come carbon's not 12.00000 ad infinitum? Well, the reason for that is this, that in nature, there are several variations of the carbon nucleus. Those are known as isotopes of carbon. Now, they all have 8 protons. Here's the first one. This is the picture of the carbon-12 nucleus. And the notation is down here below the picture. A 12 upstairs tells you how many items in the nucleus. And then over here, here's the full isotopic notation. 12 items in the nucleus, and then down here, 6 of them being protons. That completely identifies the element. But that's not the only one that we find in nature. Here's another variation, another isotope, carbon-13. We can find these. Matter of fact, carbon-13 and carbon-14 are involved with what we call radiometric dating. They're radioactive nuclei. Now, they're not deadly or anything like that, but they decay spontaneously at a specific rate. And actually, these isotopes are formed in the upper atmosphere of Earth by regular carbon atoms being nuclei being struck by cosmic rays from outer space. Space is filled with these high energy particles called cosmic rays, and when they intersect with the nucleus of carbon, they can change it into a carbon-13 or a carbon-14, and then these decay. Now, this is the most abundant isotope in nature. Okay, this is the one, it's like 99 point something percent of all the carbon is good old 6 plus 6, carbon-12. And this is the one that they use to define the atomic mass unit. But these two can be found. It's not hard. Matter of fact, you've got some carbon-13 in your body right now. Anything that is alive has got carbon-13 in it. All right? And from anything that breathes, I should say. Anything that's alive and breathes oxygen from the atmosphere has carbon-13 in it. But these are the rare ones. So that number, 12.011, that number is a reflection of the fact that most of the carbon in our world that we can observe is 12, but there's a little bit of the heavier carbon, and so the average mass is a little bit over 12. All right, let me repeat that. 12.011 indicates that there's a little bit of the heavy carbon in nature, and it brings the average mass to about 12.011. Now, if carbon-12 were the only isotope in nature, then the mass number down there at the bottom would be 12.00. But we got these other two guys, not a whole lot, but enough that we can measure it. And that's what that 12.011 indicates. So let's get back to this molecule discussion. Here's oxygen. Here's another polar molecule. This one, the blue end up here, where the arrow is in the upper right corner, the unbound, the unshared electrons tend to hang out up here, making this a negative end, and the two H's tend to be positive. A proton out here, and then somewhere between the hydrogen atom and the oxygen atom is a shared electron, what we would call a valence electron. Now, this is water. Water is a 16. Hydrogens are 1. So the atomic mass is about 18 atomic mass units for H2O. All right? And you can read that off on the periodic table. And if you're and this one's rounded off. I mean, we could, get down to some, and we will in a second with another compound. So one of the things about this, you would say that 1 metric system mole of water has a mass of 18 grams. Okay, so the metric system bulk, huge bulk, shapeless blob, is actually, well, it's maybe shapeless, but it's definitely set so that a certain number of atoms of carbon weigh exactly 18 grams, and that's what the mole is. So a molecule is one of them. A mole is the shapeless bulk of, that adds up to 18 grams. So whatever the atomic mass unit is, 1 mole, which is roughly 6.022 times 10 to the 23, is equal to 18 grams. All right? And that number, 6.022, is known as Avogadro's number. And you can read more about it in the additional readings page inside web courses. I've got links for all of that stuff. Okay. So the mole, it's a strange term, but it's based on our conviction that the atoms that we cannot see make up a certain mass of atmosphere that we actually do breathe. And you can measure the weight of air. You just can't measure the weight very easily anyways of individual molecules. All right, let's do an example together. And then you're going to do this on clickers. Silicon dioxide. Let's look at this baby. Okay, let's get the mass of 6.022 times 10 to the 23 silicon dioxide molecules, SiO2. Silicon dioxide, also known as silica. And its chemical formula, SiO2, that means one silicon and two oxygens. So, and from this periodic table, oxygen is about 15.99. And we got two of them, all right? And then one of the silicons, and hey, you guys, look, 28.086. That means that there's some isotopes of silicon that are a little bit heavier than 28. Right? So there's some, I guess there's some 29s. I haven't looked up silicon lately, but anyways, from the periodic table, there you go. So silicon dioxide is going to be two of those. So here's your stack of numbers over here. 15.99 plus 15.99 plus the silicon mass, 28.086. And that adds up to 60.084. Okay? Now, if you have one SiO2 molecule, its mass is 60.084 AMU. Right, so write down that sentence. One SiO2 molecule has a mass of 60.084 AMU. Right, now the molecule, the cule of the mole is 60.084 AMUs. Right? It's 3 atoms and an atomic mass unit 60.084. A mole has a molar mass of 60.084 grams. Right? So that's how you figure out the gram level of a full mole. Now a mole, 6.022 times 10 to the 23 silicon dioxide particles, 60 grams, that's a little chunk of silicon dioxide. Oh, by the way, another word for silicon dioxide, quartz. Have you ever seen a quartz crystal and held it? Yeah, that's silicon dioxide, SiO2. And here's Avogadro's number, N subscript A, 6, and we know it actually, we know it to a few more significant figures, but 6.02 times 10 to the 23, it's a big, huge number. And that's the number of atoms or molecules in a mole, a shapeless bulk, Latin root word moles, of anything. And that's in the metric system, all right? In the metric system, we design or we figure this number out by saying, all right, I want 12 grams of carbon. Let me try to count or estimate the number of molecules in there. And there's ways to do that with X-ray diffraction and stuff like that, counting molecules. We can do it. So it's 6.022 and then a bunch of other digits times 10 to the 23. It's a huge number. All right, now, I want to show you something else about silicon dioxide. So let's talk about this compound, SiO2, for just another minute. Here's a U.S. patent that I looked up yesterday from the U.S. Patent Office. And let me just do a close-up here. Inventor Samuel Mark Gillette from Burlington, North Carolina. This is from 1999. Laundry detergent compositions containing silica for laundry detergent sheets. Okay, nice. So silica, laundry detergent, nice. All right. So make a note of it. Silica, I mean, it's a compound. It's very common. And apparently Samuel Mark Gillette invented this patent for something that Uses silicon for laundry detergent sheets. Here's another one. Protein shakes. Nice. I looked this one up on the internets yesterday. I've never tried this flavor, but it's strawberry cream. That sounds pretty nice. Here's the nutrition facts. Let's focus in on these ingredients over here. All right, and you can see in there vitamin E, sea salt, acidophilus, chromium amino acid, chelate, silicon dioxide. So you might be saying, oh, Dr. B, not only can you clean detergent, you can clean laundry with it, but you could put it in your protein shake. But guess what, guys? Silicon dioxide, another name for it, is sand. So you got to ask yourself, why are they putting sand in your protein shake? I'm not sure I want to buy any of this stuff. And my wonderful students, I want you to be very vigilant about looking at ingredients of stuff like this. Here's another one, detergents. We saw that patent, the detergent sheets. Used to be able to go to the store and look at powdered detergents like Tide and stuff like that. And if you look on the ingredients, they don't have it anymore. The first place I looked yesterday for this was the Tide website. Tide doesn't have silicon dioxide in there anymore, but they used to. Putting sand in your clothing. What is that? But anyways, that's what they do. All right, so be mindful, be vigilant. Try not to consume silicon dioxide. Another one, most of this stuff actually is pretty good. But there's another one, ethylene glycol. You see that in ice cream and stuff. It's a thickener. You know what else they use it for? Antifreeze, coolant in your radiator system in your car. It'll kill dogs. It's sweet and it's thick. And it's used to thicken stuff like ice cream. And it'll kill a dog. Dogs like it. If you spill antifreeze in your garage or something, make sure you clean it up or there's no dogs around because they'll lick it and it'll kill them. But we put it in our ice cream. I don't know. The cheap ice cream, I guess. All right, let's try a different compound. Let's see what you guys can do. Oh, by the way, we don't have clicker base, so just go ahead and write down the question. And you can click if you want, but I'm not listening. I forgot my clicker base, my listener, my receiver over in my office. It's been one of those days. But let's try good old CO2. Go ahead and compute the molar mass of carbon dioxide, CO2. Yeah, you can't use your clicker, sorry. But do use your pencil and paper, just figure it out. "20 seconds. I'm going to ask for a show of hands. 10, 9, 8, 7, 6. This is interesting. People are leaving now that they know I'm not clicking. I lost count. 5, 4, 3, 2, 1, 0. Who votes for A? Who votes for B? You sure? 12.011 AMUs? Okay. Who votes for C? For 40, the molar mass. Are you sure it's not E? What is E the answer for? No, it's not the atomic mass. It's the mass of one molecule of CO2. All right, so C is correct. All right, so mark down C, 44.09, 44.009. Two more people sneaking out. See, that's why they want me to use clickers, but I like them because... So I don't really care if they leave. It's fine. I know who they are. All right, let's talk about electron orbitals. My animation's a little bit messed up here. Let me get rid of that. We're going to talk about the orbitals of carbon. A carbon atom. We've just been talking about carbon. CO2. Now, there's two energy levels that are occupied by electrons in the carbon atom. The first one is the n equals 1. Now, this is different from n equals 1 for hydrogen. Hydrogen's got 1 proton. Carbon has got a lot stronger attraction. It's got 6 protons in the nucleus. All right? Now, the orbital angular momentum is actually 0 in the lowest energy level, n equals 1. And that's like an object, if you were thinking about the nucleus as a planet, an object that has no angular momentum is like going to the North Pole and throwing a ball straight up in the air. It doesn't acquire any angular momentum or spin from the Earth's spin. And if you throw it straight up, it's going to come straight back down and land on the North Pole. Now, if you throw it south in any direction, it's going to have some angular momentum relative to the Earth. All right? But if it goes straight up, it's going to come straight back down and land right on your coconut. All right? So that's kind of an L equals 0 angular momentum state. Now, each of the electrons have intrinsic spin, and the traditional symbol is up and down. But you can think of the two arrows there. But you can think of it as clockwise spinning or counterclockwise spinning. All right? So the total population of electrons, there's just 2 in the n equals 1 energy level. All right? There's no angular momentum states. And so these are just straight pop-ups. Okay? Very simple shape. They don't have any directionality. They're just kind of a spherical distribution of energy. And so there they are. Okay? So put my +6 there, the red +6 in the middle signifies the nucleus for the carbon. All right. Now, I want to have a neutral carbon atom, so I need to park another 4 electrons in the n equals 2 level. All right. So let's talk about n equals 2. All right. We got 2 down in the n equals 1, and that's all we can do. That energy level is full. Go ahead and make a note of that. So this is 1D. Energy level is full. All right. Now, we're not going to be able to fill energy level n equals 2, but we're going to get it halfway there. So let's take a look at what we got. Okay, orbital angular momentum can be 0. You can have some pop-ups at this energy. Okay, it's a pop-up. You can think of it as a L equals 0 pop-up that goes a little bit higher before it comes back down. A little bit more energy. N equals 2. But it's a straight pop-up from the North Pole. Now, the other angular momentum you can have is L equals 1. And really, this is in units of Planck's constant. So Planck's constant divided by 2 for electrons. Anyways, now the L equals 1 level, or the L equal 1 orbital angular momentum state, can be split by a magnetic field. So if you put a carbon atom in a magnetic field, you'll see its N equals 2 spectral lines splitting into 3 really close spectral lines, almost the exact same color, but not quite. We can split them apart. The stronger the magnetic field, and that's related to the spatial distribution. So there are 3 suborbitals at N equals 2. And in each of those suborbitals, there's another 2 electrons possible, a spin-up electron and a spin-down electron. Okay, a clockwise and a counterclockwise intrinsic spin. All right, so that means that in energy level N equals 2, we actually have 8 possible orbital states. We have the L equals 0, that's 2. All right, and then we have the L equals 1, 3 suborbitals, and they're perpendicular. So they're like the X and the Y and the Z axes. You could think of them that way. They're perpendicular to each other. And one of them is spin up and one of them is spin down in each of those. So that's another 6, total of 8. But carbon only, for a neutral carbon atom, okay, not an ion, but a neutral, you want 6. Now you already got 2 of them down here in N equals 1. All right? So of these 8 possibles up here, you only need 4. So we're going to blaze 2 of those out. All right, let's see if we can. There we go. All right, so that is what we've got. All right? 4 of the states are unfilled. Now what that means is carbon will like to, I'll express it this way. Carbon would like to have those 4 electron orbital states full. It would like to have 4 more electrons. It can borrow them from a hydrogen, from an oxygen, from anything else that's got electrons. And that is how carbon makes a molecule, CO2. Carbon dioxide, 2 oxygens. Oxygen, it shares 2 oxygen atoms from one of the oxygens, and it shares another 2 electrons from the other of the 2 in carbon dioxide. And it now has a full 8, but only as a compound. And that's how compounds form. The 4 that we have over here, those could be shared with some other compound. Those are called valence electrons. Right? And they're also used in bonding. So you have 4 gaps that will allow carbon to bond with something. And or you can think of it as 4 valence electrons that it can share out, with another molecule or with another atom. All right, and that's how bonding takes place. We basically, for covalent bonding, you share the outer electrons with another atom that's not full, that doesn't have a full energy level. All right. So let's talk more about bonding. All right. Here's the main idea. Other elements react chemically, either gaining or losing electrons to attain a filled outermost energy level, the same outermost energy level as the noble gases. Now, I haven't mentioned that term. Let's take a look at the noble gases in the periodic table. All right, and what we're going to do, so carbon is going to either lose two or share two of its electrons, and then it's going to look more like a helium. Or it's going to gain four more electrons, and it's going to look more like a neon. Let's look at that. Okay, over here in the far right column of the periodic table, these are the noble gases. And these are the atoms for which the energy level is completely full. All right? Now, helium is the atom that has 2 electrons in n equals 1, and that's it. Okay? It's got 2 protons in its nucleus, and it loves to have 2 n equals 1 electrons. And when it does, it's happy as the proverbial clam. Okay, atoms like to be neutral. If they're not neutral, if they're ionized, they'll either attract another electron if they're positive, or they'll lose that extra electron they have to something else, and they'll try to neutralize each other. All right. Now, what we're going to do here is look at this guy here, chlorine. Now, chlorine is 1 notch away from argon. This is another noble gas. Oh, by the way, let's go to the second level here. Let's look at the second level. Okay, here's the second row. So now we're filling up the n equals 2. So here's the 2 elements here, lithium and beryllium. N equals 2. These are the ones where you fill the L equals 0 orbitals. But you have 6 more that you can fill at n equals 2, and those are out here. Right? And Ne, neon, represents a completely full energy level. Carbon is not. Carbon's here. It's kind of in the middle of things. It could, if you give carbon 4 more, its electrons will look like the electrons of neon. If you strip 4 from carbon, it'll go back to boron, back to beryllium, back to lithium, and all the way back over here to helium. So if you strip 4 of those, or somebody steals those 4 from a carbon, it'll be happy because it'll be in the helium electron orbital configuration. So atoms like to be in some configuration that makes their electrons anyways fill up all the energy levels so that they're like helium, neon, argon, krypton from kryptonite. You thought kryptonite was just something in the comic books? No. Krypton, it's a real element. Xenon, radon, and this other stuff down here. Element number 118. Which I don't think they've found. Some of these they have found. Anyways, they're still looking for these elements down here, the UU elements. Anyways, chlorine here. Chlorine, atomic number is 17. That means 17 protons in its nucleus. Almost full. Sodium, atomic number 11. Okay, it's out there. It's got everything that helium's got. It's got everything that neon's got, and it's got 1 more electron. And that's what a neutral sodium atom will look like. So make a note of it. And sodium, Na, has 1 stray, loosely bound electron. That is its valence electron. It is very easy to steal. Chlorine, over here, oh baby, chlorine is sitting there. Oh, if I could just get 1 electron, I'll have all my energy levels filled. I'll still be chlorine, but my electrons will think they're sitting around an argon atom, because my energy levels will be filled. So Chlorine is over here. Oh man, let me find just one electron. And sodium's over here. Oh man, I gotta be careful. My electrons, somebody's gonna, it's hanging out of halfway out of my back pocket. Somebody can. And so what happens? Well, those two, the chlorine steals that valence electron from sodium. Sodium becomes a positive ion, Na+. So write down Na+. And chlorine becomes a negative ion because it's got one extra electron, Cl-. And they attract each other. Positives attract negatives. And they form an ionic compound called salt, table salt, NaCl. Right? So that's another way that atoms can form compounds by an ionic bond, right? By stealing electrons. Now, CO2, carbon dioxide forms shared electrons. They don't steal. So they have constructive interference. We'll be going through that in just a second. But this is the drama of chlorine and sodium. And here's the interesting thing. Sodium, you can make a note of this. Sodium, when it's exposed to air, sodium metal, metallic sodium, when it's exposed to air, will explode. My chemistry teacher in high school, Dr. Cooper, was handling some metallic sodium in the back room, in the storeroom, and he accidentally exposed it to air, and it blew him across the room and set off all the fire alarms. They had to call the fire department and everything. He was okay. He was a tough old bird, but yeah, it was explosive, and it wasn't a very big piece either. Chlorine gas, chlorine. Did you know that chlorine is a weapon of mass destruction? World War I, that was a weapon of mass destruction. Poison gas, chlorine. It'll kill you. It tears apart your lungs, apparently. Very, very bad stuff. But together, when they form an ionic compound, NaCl, the salt of the earth, something we need to live. You can't live without this stuff. If you go without salt, you're going to perish. It's kind of cool. Two things that are dangerous on their own, but together they form something that we have to live. All right, let's look at carbon dioxide. All right. Now, what happens with carbon dioxide is, okay, two of the electrons from carbon in the two of the outer electrons are shared over to oxygen. Now, what that does is it makes the N=2 level for the oxygen completely full. All right? Same thing over here with this oxygen. So if you have one carbon and two oxygens, each oxygen will borrow or share two of these electrons. And now your oxygens, the outer shell, is looking like a neon outer shell. All right? There's 8 electrons there. That's just like neon. And then now, without those outer 4 valence electrons, the carbon is looking like its outermost shell is N=1. So that's like a helium outer shell. Right? So when I say that elements combine so that their outer shell is like a noble gas outer shell, this is what I mean. The two oxygens have outer shells filled like neon. The carbon has an outer shell. It's stripped, its valence shell is stripped, but the remaining shell that's left, the outer shell, is like helium's outer shell. Helium. So helium-like outer shell and neon-like outer shell for CO2. And that's how CO2 is formed, by sharing. Now this one is called covalent bonding. They actually share the electrons. They don't steal. Na and Cl steal. The Cl steals, Na loses. They become positive and negative, and they bond ionically. This one is shared. And let's talk about those forces. All right. So there's 3 types of bonding. We've talked about 2 of them. The first kind of bonding is ionic, and that's when an electron is transferred between atoms. All right, so like Na and Cl. Na loses, Cl gains, and so the electrostatic force is the binding force for that. And so that's like, KQ1, Q2 over R squared. And that's a normal, or that's an ordinary electrostatic binding force. Now, covalent bonding, that's another kind. This one is, boy, my letters are messed. Sorry, this is supposed to be 3A. The octets, the filled outer shells, are achieved through sharing of electrons. Okay, and this is typically between non-metallic elements on the right-hand side of the periodic table. Now, there's some other bond types called metallic, and this one is actually achieved when the outer valence electrons move freely throughout the metal. That has a bonding effect, and they call it an electron gas within a rigid metal, a rigid lattice of metal atoms. And the interesting thing about metallic bonds, not only are they mediated by electrons, but they have the effect of conducting heat and electricity pretty well. Although metallic bonds are very difficult to model mathematically. Covalent bonds we can model fairly good. So make a note, covalent bonds can be modeled by looking at the wave function of the electron. The de Broglie wave function, the de Broglie wave around the nucleus and in the internuclear system known as a molecule. So we're going to look at covalent bonding here. All right. Now, for an electron, when 2 hydrogens are far apart, their waves don't overlap. Okay, these 2 shapes show the intensity of waves of the L equals 0 electron. That's the straight pop-up from the North Pole. It doesn't have any directionality. It just diminishes as the distance increases from the nucleus. So when they're far apart, the wave functions look like this. Here's one atom over here on the left. Here's another atom over here on the right. When they get closer, the wave functions overlap. Okay? And that's where you get constructive interference. So now my 2 atoms are closer, and look where I've got my cursor. Right here in this little valley between the 2 peaks. Now, we didn't have that before. We had a really deep, it went all the way down to sea level in this upper picture. Right up here by the word symmetric, you're back down to sea level. But when the atoms get closer, the 2 waves add together. You get constructive interference right here. And here's the square of that wave function. Okay? And that is where bonding happens, right here, right between the atoms. The electron is in the de Broglie wave interpretation, where the amplitude of the wave is strong, it is probable that you will find the electron. Where the amplitude is small, like over here in the first picture, you're not going to find an electron over there. Right here, sea level between these 2. But down here, yeah, you got a big amplitude. Here's the square of the amplitude. And you got a lot of amplitude in here in the middle, and that's where you're going to find your electron. Okay, they're sharing an electron, and that has the effect of binding. All right, so you got to do a lot of lovely calculus, you know, buku calculus. You got to use imaginary numbers, and you may say to yourself, Dr. B, get out of town. What is an imaginary number? Well, an imaginary number, if you don't remember from high school geometry class, is all numbers that are the square root of a negative number. So the square root of -1 is equal to, let me get back here. The square root of -1 is equal to the letter I. We use a symbol for it, the letter I. Okay, so I squared is equal to -1. Now, we're not going to do any imaginary numbers. I'm just using that as a vocabulary term. Calculus, imaginary numbers, not much trig, though. And you can figure out how all this stuff bonds together. Now, another topic is electronegativity. And, oops, forget about this indication here. This is from the old textbook, 911. I'll remove that for the next lecture. But definitely, let's talk about this. Here's a concept. If an atom has a much greater electron pulling activity than another atom, the electron is pulled completely away from the atom with lesser pulling activity, and an ionic bond will result. Now, an example of that is sodium and chlorine. Chlorine has a bigger electron pulling ability, and that's called electronegativity. The electronegativity is the fancy physics word for the ability to steal electrons from another atom or another molecule. Now that's reflected here, okay? They don't overlap. You know, these kind of blobs here are supposed to indicate wave functions. It's not very good on the display, but the wave functions are separate. So this is like the two peaks that go all the way down to sea level. Right here, they're in between this bottom figure here where my cursor is. There's no wave function there. You're not going to find the electron there. The electron is going to be over on the left or over on the right, but not in between. Now, if the electron pulling ability is more even, then you get something like a covalent. This one is wave functions overlapping. And here's one, polar covalent, where one of them is a little bit stronger than the other. All right? So if electron pulling ability is more even, the electron is shared. You have constructive interference, a purely quantum effect, and that's known as a covalent bond. Electronegativity is the comparative ability of atoms to attract bonding electrons. All right? And I'm going to give you a table that you can, not figure 911, but definitely look at this table and read in page 288. Oh boy, this one says figure 910. I thought I got rid of that. Okay. This is like a periodic table, and below each chemical symbol here is the electronegativity. Now, all the way over here, here's chlorine, 3.0. So it has a relatively high electronegativity. And here's sodium over here, 0.9, very pokey. All right? And that means that sodium and chlorine together are going to have an ionic bond. But now, here's carbon and oxygen, 2.5 for carbon, 3.5 for oxygen. That's not a big difference. So you're going to have covalent bonding there. The electronegativity level allows you to judge whether you're going to have an ionic bond or a covalent bond. So let's look at chlorine and sodium. Here they are. Ignore that inscription, figure 910. That's from the old textbook. But we can still look at the diagram. All right, so here's sodium over here, chlorine over on the right. All right, and write down the delta, the change in the electronegativity, the difference in the electronegativity is 2.1. Now, when you have that big of a difference in electronegativity, ching, you're going to have an ionic bond. Good, strong ionic bond. All right? Now, let's go to the next comparison. All right, let's look at carbon and oxygen. All right, 2.5 and 3.5, as I just pointed out. All right, now for these two babies, the difference in electronegativity is just 1.0. All right, so there's a little bit of difference, but not a huge difference. That's going to be a covalent bond. All right. And here's the general principle. Okay, you can jot this down. If the difference in the electronegativity is 1.7 or more, then you're going to have an ionic bond. If it's 0.5 or less, then it's going to be a covalent bond. If it's between 0.5 and 1.7, it's going to be a polar covalent. So there's going to be a little structure to it. Carbon and oxygen will have a polar covalent bond. Right? Right, so jot that down. I'm going to ask you a little IQ test question. This is, we don't have clicking going. We'll do this before we dismiss. Okay, 1.7 or greater, ionic. 0.5 or less, covalent. In between, polar covalent. All right, here we go. Here's a question for you. Which element can magnesium Mg form, with which element can magnesium Mg form an ionic bond? Hydrogen, beryllium, sulfur, silicon, oxygen, or chuctanium? Mg. How many people vote for A? Nobody? How many people vote for B, beryllium? I see one hand, good. How many vote for sulfur? C. Okay. How many, see you, dear. How many vote for silicon? Has that got a more than 1.7 difference? Yeah, I see a couple people. And actually, all of those babies are good. The only one that it doesn't, magnesium doesn't form an ionic bond with oxygen. And of course, there's no such thing as chuctanium, so far as we know. Now, magnesium and oxygen, they do form a compound. Ever heard of milk of magnesia? Yeah, that's magnesium oxide. Yeah. Oh, wait a minute. Oh, right. So actually, these are the wrong answers here. All right, good. So I had to borrow this quickly before class from one of my old lectures. Yeah, so these are the wrong answers. Okay, good. Thank you for pointing that out. Good. Magnesium oxide, yeah. Next time we'll talk about some more important molecules. You'll have some homework tonight. I'll see you on Thursday. You're dismissed. Ooh, Dr. B, thank you for catching that. Where's my cursor?